Hello. In this video I'll provide an overview of our team's project which implements a roadmap navigation system which finds the shortest path between towns. In our case it's Irish towns. So the project uses two different types of priority queues. It uses a binary heap and a Fibonacci heap, both implementations of the priority queue. So I'll provide a high-level overview of our classes and interfaces and their most important methods, as well as how they interact with each other to solve our problem. So the first thing I want to look at is the priority queue interface, which is really simple. It just defines the basic operations that any priority queue is going to have. You can add elements, you can remove elements, check the size, check if it's empty, and get the minimum element, or remove the minimum element. Then we've got this populate down here, which does what it sounds like. It just fills the priority queue with an array of keys and values. So of course it accepts these two generics k and v, where k is going to be the priority of the element in the queue and v is its actual value. Next thing up is the default comparator, which again is really simple. So of course we need in our priority queue a way to compare the elements, which is this. It just receives two generics, element A and element B, compares the two and tells you which is bigger. Next up is the AbstractPriorityQueue. Within this we've got this inner class entry to define an entry in the queue, which implements this entry, which all that does is has two values for get key and get value. A couple of more methods to talk about in here. So we're providing partial implementations of the priority queue interface here because this is an abstract class. It has this comparator object comp, which is used to compare the keys of the entries in the priority queue, which coincides with this method compare, which is just used to compare two entities in the queue and tell us which is more important, which takes priority. It has this check key method, which we use to compare a key with itself and find out if it's valid using the comparator. We don't provide implementations of everything in the priority queue interface here. We don't have size, insert, we don't have remove, min, or populate. We just leave those methods as abstract so that any concrete class that extends this abstract priority queue can provide their own implementation for that method. Next up is the HeapPriorityQueue, a concrete implementation of the abstract priority queue. Okay, so this one it's a concrete implementation of a priority queue using a binary heap. So it extends the abstract priority queue and it provides an implementation for the method that we declared in the priority queue interface. This class starts off with an array list of entry objects, which is the heap, in which every element is going to be represented by a key value pair, which is an entry. We've got a couple of methods then to talk about. We've got this populate, which we saw in the interface previously, which populates the priority queue with its key and values. We've got all the methods that we'd expect to have implemented as we saw in the interface. We've got insert. We've got insert down here to insert a new key value pair into the queue. We've got min. We've got remove min to remove the smallest element from the queue. We've got this concept in the heap, which is known as the heap property, which says that the key of each entry is going to have to be greater than or equal to the key of its parent. And that property ensures that the minimum entry can always be found at the top of the heap. So we've got a lot of methods in here which are sort of used to reinforce that or to enforce that principle. So we've got this parent, which returns the index of the parent at index j in the heap. We've got left and right, which return the indices of the left and right children of the node at index j, respectively. We've got swap over here, which swaps the entries at indices I and j. So we take whatever was at I is at position j, whatever was at j is at position I. We've got upheap, which is used to restore the heap property after an entry has been inserted at index j. Because you insert an entry, it's going to get messed up, this heap property, so we use upheap to restore that. It does that by swapping the entry at j with its parent if the entry's key is less than the parent's key. And then it just continues up the heap until it finds a parent which is less than or equal to the entry, or until it reaches the top of the heap. We've got down heap then, kind of similar. That method is again used to restore the heap property after the minimum entry has been removed. So the previous slide we saw that an entry has been inserted. This is if something has been removed. So if an entry has been removed from the top of the heap, then this just swaps the entry at index j with the smaller child if the child's entry is greater than the child's key. And it continues down the heap until it finds a child that's greater than or equal to the entry, or until it reaches the bottom of the heap. We've got heapify. which is going to build the heap by repeatedly calling down heap on each entry in the heap. So we're looping through and calling down heap until we reach a child that is greater than or equal to the entry that we're looking at, or until it reaches the bottom of the heap. So we have heapify, which builds the heap by repeatedly calling down heap. So you can see it loops through the heap, calls down heap over and over again until it works its way up to the top. And this just ensures that the heap property is satisfied for all entries. Next thing to look at is the tree. So the tree is part of the Fibonacci Heap implementation. So in the Fibonacci tree, each instance of the tree class represents one of the trees in the Fibonacci heap. It's got this inner class tree entry, which again, like in the class we looked at there a second ago, implements the entry interface. Again, pretty much the same as the last time. This represents a key value pair in the tree. The key is used to determine the order of the entries in the tree, and the value is the data associated with the key. What to look at in here, we've got several, I suppose, key methods. We have getDegree. GetDegree is here. And this returns the degree of the tree, where the degree is kind of like the number of layers that are in the tree. We have getKey, which returns the key of the entry that we're looking at the root of the tree. We have getChildren, which returns the list of children of the root of the tree. We have setDegree, which is going to update the degree. And we have addChild, which is going to add a child to the root of our tree. We have some checks in here to say that if the degree of a child is greater than or equal to the degree of the tree, then it's going to increase the degree of the tree. Next up then, I suppose, is the Fibonacci heap, which is a fairly long class. So the Fibonacci heap is a concrete implementation of a priority queue, again, which uses a Fibonacci heap data structure instead of a binary heap. So it implements the PriorityQueue interface and provides implementations of all the methods we declared in there. This class maintains a list of tree objects. So we have this array list tree, where each tree is going to represent a tree in the Fibonacci heap, which is the same as what we saw in the tree previously there. Some key methods that we have in here. Okay, we have populate, which again, we're implementing this from our interface. It's going to populate the priority queue with an array of keys and values. We have all the methods that we're expecting to see now at this point. We have insert to find the minimum value, get the max degree to find the highest degree in the tree. Methods, I suppose, particularly worth talking about here. We have getMin, which is going to iterate over all the trees in the heap and return the tree with the smallest root, so we can find the minimum entry in the heap that way. GetMaxDegree, I suppose, is self-explanatory, but it iterates over all the trees in the heap and it returns the maximum degree among them. So you say return max degree. I mentioned previously there that the degree of a tree is the number of its children, so sort of like the number of layers in it. This method here, getMaxDegree, is used in the cleanup phase of the tree to create an array of trees indexed by degree. So I suppose we'll look at cleanup then. Okay. Cleanup, it accepts this int max degree. So it's going to be called after the minimum entry is removed from the heap. And the job of this function is to merge all the trees in the heap that have the same degree. So it ensures that no two trees in our heap are going to have the same degree after this method is finished. And this is done by creating a temporary array of the trees indexed by degree and then iterating over all the trees in the heap. This method then merges the two trees and it continues this process until no two trees are remaining with the same degree. So you can see it uses this merge method. To look at that, just above here we have merge. So merge accepts an array of degree trees and a tree object, which is new tree. So this merges a new tree with an existing tree of the same degree in the degree trees array. If the new tree's root is smaller, then it becomes the child of the existing tree, or vice versa. And after merging, if there's another tree in the degree trees array with the same degree as the merge tree, then the method is going to recursively merge the merge tree with that tree. So you can see this is recursive. We have merge down here. It's going to repeatedly call itself if there's another tree in the degree trees array with the same degree. So we continue until we have until we're maintaining this heap property. Next thing to look at then is the road map, which is again quite a large class. I suppose this is our main one. This is the main class that uses the priority queue implementation to solve our problem of finding the shortest path between towns on a road map. Okay, so in the road map class we have two inner classes to talk about. We have the town and we have the road. So the town, we've got a couple of different fields here. We have the name of the town, we have the distance, which is the shortest known distance from the start town to this town. We have visited, which is just a boolean to indicate whether the town has been visited in our shortest path algorithm. We have roads, which is going to be a list of roads connected to the town. And we have shortest path, which is going to be a list of towns representing the shortest path from the start town to this town. So let's say, for example, we have Cork City to Charleville to Kilkenny to Dublin, or whatever it might be. It also has a couple of methods for getting and setting these fields, obviously, as well as a compare-to method, which is used for comparing one town to another based on their names. The road inner class then is quite similar. In here we have towns, which is a set of two towns that the road connects. So it's going to be one town, no, town A, town B. We have the length of the road in question, which I suppose isn't obvious from the name there. It's the length of the road. We have visited again, same as the town, to indicate whether this road has been visited or not in our shortest path algorithm. And again, obviously this class has methods for setting these fields and marking the road as visited. It also has another compare-to method for comparing this road to another by name. That's it for our inner classes. So to talk about some of the attributes of the road map itself, we have heap type, which is just going to be the type of priority queue we're going to use. It's either going to be a binary heap or a Fibonacci heap. We have a list of the towns which are going to be used in the road map, a list of the town names, and a list of all the roads in the road map. For some of the functions to look at, we have a lot of helper methods to skip over, I suppose. We have what are basically abstractions away from the priority queue, just in the context of our map. Okay, we've got import map, which accepts a file path, and that's just used to import a CSV. And the map then is represented as a list of roads, where each road is a line in the CSV file. So we can look at this in our example here. We have this map data CSV. Yeah, so every line here is going to be a road. We have extract towns and roads to iterate through all those lines and add them to our list of towns and list of roads. We have add town to add a town to our list of towns, add road, which is the same thing just for roads. We've got shortest path from a town to a town, and this method just finds the shortest path between two given towns and it returns a string representation of the path, so a minimum distance from place to place and then the actual distance in kilometers. Find shortest route. This is a fairly involved one. So this takes the from town and the to town, and it finds the shortest route between two given towns using the Dijkstra's algorithm. It uses a priority queue to keep track of the towns that need to be visited, and it updates the shortest known distance to each town as it goes along. New priority queue, that's sort of what it sounds like. This creates a new priority queue of a specified type. So we pass in the type of the heap that we want. It's going to be either priority or Fibonacci. Get roads to check. This takes in a town to check and it returns a priority queue of all the roads connected to a given town, where the roads have been ordered by their length. Get routes to check. This method adds all the towns connected to a given town to the routes to check priority queue. And if the distance to the town through the given town is less than the currently known shortest distance to the town, then it'll reset the map by marking all the towns and roads as unvisited and setting the distance to each town to infinity. So we can see what I just talked about there. We have this reset map, which does what I just described, where it takes all the marked towns and roads and sets them as unvisited and then sets the distance to each town to infinity with this integer.max value. Route names, then, this just returns a string representation of a given route. So I suppose now I realise that I skimmed over a lot of that, but this is quite a long class. I couldn't really talk about Dijkstra's algorithm in this video, it's already quite long. So let's just demonstrate what this project actually does. I've got my roadmap, and let's run this. Okay, so we've iterated through all the routes that we have in our CSV file, and we've got quite a lot of them. Let's just take, for example, there we've got from Dundalk to Ennis. We found in total we have 348 kilometres. We have all the stops in between: Dundalk to Drogheda to Balbriggan to Dublin to Naas to Newbridge to Portlaoise to Limerick to Ennis. And that's pretty much it. So thank you for watching, and as I say, hopefully that was informative for our implementation of pathfinding on maps.